Yeah, hi everyone. My name is Christian. I'm a PhD student at TU Delft. So today I want to talk about one of the outputs of my PhD project, in which I have used PyPSA. So the title of my presentation is Technology Configurations for Decarbonizing Residential Heat Supply through District Heating and Implications for the Electricity Network. I would like to give a little bit of background. So if we look at the first figure on the left-hand side, we see a breakdown of the final energy consumption by sector in the European Union in 2023. And what stands out is that the building sector, which constitutes of the households and services, account for about 40% of energy consumption in the EU. And most of this is used for heating. If we take an example of the breakdown of household energy use by end use, we can see that uh, most of the energy consumed is used for space heating and water heating. The bad news here is that about 2/3 of the heat supply in buildings in the EU is still based on fossil fuels. And if we look at individual member states, such as the Netherlands, it's up to over 85 to 90% of residential heat is still met by natural gas. So this implies that in order to achieve the energy transition goals, we must decarbonize residential heat supply as well. And one of the important technologies, or one of the key technologies that will play an important role in decarbonizing residential heat supply, is district heating. And this is because district heating can integrate diverse sources of heat sources, such as renewable geothermal heat sources, waste heat from industries, and it can also enable the integration of large-scale thermal energy storage. And more importantly, we know that most of the buildings in the EU, over 40% of the buildings were constructed before the 1960s, and over 90% of buildings were constructed before the 1990s. So most of the buildings are quite old and poorly insulated. District heating, therefore, is a suitable technology to provide to meet user temperature preferences in buildings that are poorly insulated without needing any retrofitting. But as we can see here, some of the heat sources that we might want to integrate in district heating include geothermal or heat pumps or electric boilers do require some electricity to produce their heat, or at least require electricity to upgrade supply temperatures. So decarbonizing district heating also tends to increase the interactions between heat and electricity network. So it becomes essential to assess the impact of decarbonizing district heating on the electricity network. So the question we set to answer was, what is the impact of decarbonizing district heating on the electricity grid? So a little bit on the methodology. What we did here is that we combined optimization and power flow simulations. So basically, we did a sublinking of PyPSA of the district heating network optimization model implemented in PyPSA and Panda Power for the electricity distribution network model. Indeed, PyPSA can also do power flow, but the model we got from the industrial partners was already in the Panda Power. So we thought of actually just soft linking them. So here in the district heating network model, we do an overnight investment, optimization of investment and operation. And for the MGA, we implemented the SPORES algorithm, which was originally proposed by Francesco Lombardi and was initially implemented in Calliope. So I've been using PyPSA most of the time. So I thought of kind of like implementing the SPORES algorithm into PyPSA. So that's what I did. And the reason PyPSA also has MGA, but the reason I really like SPORES is the fact that it really focuses on the spatial explicitness and distinctiveness of the near optimal solution. So I found it very interesting to work with that. So for the case study here, I looked at one of the largest district heating network in South Holland with a peak demand of over 1,400 megawatts and an annual energy demand of over 2,500 gigawatt hour. For the local electricity network, it consists of a fairly large network with about 14 transformers and 25 lines. We also included in the analysis, as you can see here, the black loads here are mostly, the black arrows here are loads that are not from the district heating network, basically to have an assessment of the overall grid impact from broader electrification. And yeah, for what we also did here is that we generated over 3,600 SPORES. The SPORES are basically the near optimal district heating network designs. And that's over different scenarios. So we have the default scenario, and then we have like high heat demand, low heat demand, different weather years, and then we have different slacks for the MGA runs. And we use SnakeMake to manage the entire workflow. So I would like to present the results by looking at first the least cost solution. So in the first figure we see here is the technology mix that we get from running the least cost optimization, which serves as an anchor over which we probe the near feasible, the near optimal space. So what at least stood up here, that stands out here, is that if we look at the deployment of technologies, we see quite a lot of electric boilers being deployed, obviously due to their low investment cost. And yeah, so once we get the input from the optimization results from the heat network, we get the dispatch of the electric boilers over the entire network. We feed that into Panda Power, and when we run the power flow, we can come up with this kind of loading duration curve for transformers and lines. Here we show only 2 transformers and 2 lines. Obviously, we can see here that the electric boilers tend to really overstress the network. But what interesting aspect also beside the electricity network we're looking at is if we look at the spatial deployment of geothermal in the heat network, we see that most over basically 4 of the geothermal wells or the geothermal heat sources are kind of concentrated in The Hague. So the good thing with MJ is that we can actually try to look for solutions that are actually very different from what we have now, right? Because right now we could say that having a lot of geothermal well in a single geographical location or in a single city might kind of like face social resistance issues. So in a case, if we want to look for a different system in which, for a different solution in which, for instance, we want geothermal, only 2 geothermal wells, that's where we can use MGA for, and the SPORES algorithm appears to be pretty powerful in looking for this. Anyway, so that was it for the least cost solution. And for the MGA results, what we see here first is a capacity utilization across all the near optimal solutions. So we can see the main aggregated units. So when we see the air heat pumps, boilers, these are the aggregated unit of all the aggregated capacity of all the different air source heat pump units in the heat network. So what we're seeing here is we're looking at the utilization frequency. So we see, for instance, that technologies such as boilers, green gas, and hydrogen can be utilized at full capacity and can also not be deployed at all in the system. Meanwhile, we see technologies such as CHPs and seasonal storage in the form of high temperature aquifer thermal energy storage. They are very rarely deployed in the system. So what we see here is that most of the technologies here are really real choices. It means beside the pipelines, you can actually do without most of the technologies, but indeed you have to substitute them with a functionally equivalent technology. If we take, for instance, we see in the least cost solution that we have a very low deployment of a air source heat pump, but indeed we have a high deployment of electric boilers. If we indeed tend to minimize the deployment of electric boilers, then we see that we kind of push more, it gets compensated by more air source heat pump. And because air source heat pump is not really dispatchable, then we tend to build a lot of storage. So these are the type of trade-offs you can analyze from this chart. But the most interesting is that we also found that the different district heating network designs really exhibit significant variations in grid impact. So looking at the second figure here on my right, what I did here is basically we defined some high-level metrics that we wanted that we tried to map into an integrated heat electricity network planning decision space. So we have, for instance, we define power to heat capacity as the combined capacity of both electric boilers and heat pumps in the system. We define, for instance, gas-based capacity from hydrogen and green gas. We define a storage pipeline and the levelized cost of heat. These are metrics on the heat network side. And for the electricity network side, we look at metrics such as the line overload events, the number of overloaded lines spread across the network. And we also look at the line loading in terms of like the magnitude. So basically, we can see the number of overloaded lines can tell us the spread of the problem, while the number of the line loading tells us the magnitude, the severity of the problem. So In gray, we see all the near optimal district heating network designs. And the pink spores basically are those designs that have an electricity network impact lower than the least cost solution. So what we see here, what we found here is that if we look at, for instance, the highest electrification design, we tend to see that actually, not because of it, not because you electrify a lot, you have a lot of power to heat capacity in your system means you tend to overload the grid. But in this case, we see that it's actually within these dashed lines, which is the lower electricity network impact compared to the least cost. So what we found in this type of solution is that it concentrates investment in either building more efficient heat pumps compared to electric boilers, or if we look at, for instance, the high electrification, it actually tends to spread out more of the electrified heat sources, such as e-boilers, and avoids concentrating them at transformers that were already congested. Obviously, this comes with a trade-off in that it has to build more pipeline capacity, as we can see here, compared to the least cost solution. Yeah, so with this, I want to conclude with reproducibility, extension, and contact. So the code is openly available on GitLab, and we've also archived the code and the data on Zenodo, and the paper is upcoming. It has been accepted in iScience, I see in press, and the preprint is also available. And with that, yeah, feel free to contact me if you have any more questions, and thank you.
Thanks a lot for the nice talk. There are some questions in the chat regarding the implementation. So which implementation did you use for PyPSA PandaPower? Did you vote that yourself? Is it included in the GitLab repository? And also the SPORES implementation. Is this both publicly available?
So the SPORES, I'll start with the SPORES. The SPORES is basically the MJ algorithm that I initially said was proposed by Francesco in Calliope. So it was also open source in Calliope, and I work on this project with Francesco. So I kind of translated that code into PyPSA. It's also openly available there. The implementation is there. And for PyPSA and the PandaPower, the code is also openly available. Just that some of the data is proprietary because we have like industrial partners, the model. You might need to feed in the data by yourself, but the code is open source.
Okay, that's great. So both publicly available in the repository,
Yes.
and because that
Yes.
might be interesting for other users as well.